Hello. All right, now we're looking at pretty much the second half of this midterm 2 review here. Let's see. So starting in chapter 4, and pretty much in this section, or this part, we're reviewing all the exponent rules. And it seems like there's so many rules, it's easy to mix them up. So this will be kind of good practice, I think. So starting with number 26, here we have x squared, y to the 5th, and that whole thing to the 8th power. So if you remember, we said if you have a couple things multiplied or divided inside parentheses, like we have, it's a x times a y, then you're free to distribute any power you want that's outside the parentheses. So we can distribute this 8th power onto the x and onto the y. We just kind of have to remember how the powers that x and y already have, the square and the 5th power, interact with that new 8th power that we're giving the x and the y. So this step right here is kind of optional. You don't have to write that out. If you remember how those powers interact with the new powers, then you should be fine. But this is an optional step, I guess. I just kind of showed that we're really distributing the 8th power onto both x and y. And now, if I focus kind of on maybe the x, I have a power to a power, so it's a second power to an 8th power. You multiply those powers. So it'd be x to the 2 times 8 would be 16. And then for y to the 5 times 8 would be 40. So that would be your answer. And you don't have to rewrite it because the directions just say simplify, and I think we've simplified. And we don't have any negative exponents. So that's the only thing you really have to watch out for is, do I have any negative exponents on my answer? If I do, I'd have to rewrite it so that there are no negative exponents. And we'll see some like that, and we'll kind of review how do you rewrite negative exponents as positive exponents. All right, so how about number 27 here? We've got 4z, that entire thing to the 0 power. So this one, I think there's kind of two ways to look at it. You could think of it as kind of similar to the previous one. You can distribute the 0 power onto both the 4 and the z if you wanted to. And then think about, okay, what's 4 to the 0 power? Well, if you remember, we had a rule that said anything to the 0 power is 1. And I think the rule kind of used a as a base. But a could represent anything. It can represent a number like 4, or it can represent a variable like z. So that means that 4 to the 0 power is 1, because anything to the 0 power is 1. And then we're multiplying by z to the 0 power is also 1. Anything to the 0 power, no matter what, is 1. So we end up with just 1 times 1, which is 1. That must be it. So that's one way to approach it, or an even simpler way, you could have just said, all right, we have 4z to the 0 power. That's what we're starting with. Well, we said anything to the 0 power is 1, even if it's something as complicated as 4z. So really, this is just 1, because you're raising something to the 0 power, and we've already said that the rule tells us that answer will be 1. So either way, you could do it the short way, where just the answer is 1 because anything to the 0 power is 1, or you could take the time to distribute the 0 power and still realize the answer is 1 either way. All right, how about number 28 now? So here we have 3a to the 11th over 12a. It's almost like you can think of it as, you can simplify the like things in the numerator and the like things in the denominator. So for example, the 3 over 12, those can reduce for sure. 3 can go into 12 4 times. So you can kind of think of it as the 3 disappears and the 12 kind of becomes a 4. So I don't know what's going to happen, but all I know is the denominator is going to have a 4 for sure. And there's going to be no number in the numerator because it's canceled. But how about the a's? Okay, if you remember, if you have a variable over a variable like we have, it's a to the 11th over a. You don't see an exponent, but it's an invisible 1. You subtract the powers. So our answer will be a to the 11 minus 1 is 10. Subtract. So I guess if you wanted to do an intermediate step, you could have said it's a to the 11 minus 1 power. You can either write that out explicitly or just do it in your head, kind of. There we go. And then the last thing, I just need to check, am I ending my problem with a negative exponent? No. Okay, so I'm good. I'm good to end right there. Okay, let's try number 29. This it's similar to the last one. It's just kind of of course, more complicated looking version. You got negative 48x, y to the 7th, And that's all over 18x to the third y to the fourth. So let's see. If you want, yeah, again, I usually just focus on the numbers, the coefficients kind of first, and then the variables. So between 48 and 18, I think the largest number that divides into both of those is 6. Is that true? I think so, yeah. And 6 goes into 48 8 times. And 6 goes into 18 3 times. Okay, so at least we know 48 can reduce to 8, and then 18 reduces to 3. So for sure my answer is going to have negative 8 over 3. And you know, if you wanted to, I left a negative in the numerator, but you could have kind of assigned it to the side of the fraction if you wanted. It could have been negative 8 over 3 with the negative on the side. It doesn't really matter. They're both the same answer. But how about we'll focus on the x's now. So x's, they can reduce or simplify, I guess I should say. And to simplify them, just like we did in the previous part, we're going to subtract their power. So it'll be x to the power of, the numerator has an x to the 1 power, so we'll start with a 1, and then subtract the power in the denominator, 3, and that'll give us the x. And if at this stage you're kind of wondering, okay, wait, but is x, now that we've combined them into 1x, is it in the numerator or the denominator? Well, at this point it's kind of in limbo. It doesn't know where it's going to go until we see whether its exponent is positive or negative. So once we subtract these two exponents, if we end up with a positive number as an exponent, it'll go in the numerator. But if we end up with a negative number in the exponent, it'll go to the denominator. As you can see, the x is going to have a negative exponent. It's going to be x to the negative 2 once I subtract those two powers. So that means it's going to go down to the denominator. It'll be downstairs with 3 instead of upstairs with 8. Let's try to do a similar thing here with the y. So we'll subtract that guy's powers. Y to the, let's see, 7 minus 2. I mean, in that one you could probably do in your head. You don't have to write that out. 7 minus 2 is 5, so it'll be y to the 5th. And since that's a positive exponent, y is going to stay upstairs in the fraction with 8 in the numerator. So the answer will be the negative 8 in the numerator over 3 in the denominator. We said y is going to the numerator because we ended with a positive exponent for y. X is going to the denominator because it had a negative exponent. And remember, if it had a negative exponent, once you move it, it now has a positive exponent. Because that's what a negative exponent tells you to do. It says, move this to the opposite side of the fraction. Once you do, it no longer has a negative exponent because you've moved it. So that would be your answer. And then again, the negative could be on the numerator or off to the side kind of the fraction. That's where you'll mostly see it, off to the side kind of right next to the fraction bar. And that one was so complicated, I'm almost surprised that number 30 looks so simple, you know? But that's okay, maybe we're getting a little break here. So it's 5x to the negative 2. I think probably the mistake that might be made is thinking, oh, this has a negative exponent, so I'm moving everything downstairs like this, 1 over 5x to the second, or something like that. But that's not true. Notice that the negative exponent, it's only on x, it's not on 5. If they were trying to indicate that the negative 2 power was on the 5 and the x, they would have put it in parentheses like this. But because there are no parentheses, they're just saying, okay, the x is to the negative 2 power, but the 5 has no power. I guess it has an invisible 1 power. But because the 5 does not have a negative power, it's not going to move. It doesn't have to move to the opposite side of the fraction, only the x does. So that would be your answer. You just move x to the opposite side of the fraction. So be a little careful. Don't move the entire thing. If you see a negative exponent, think about what is that negative exponent on. If it's not on everything, you don't move everything. You only move the parts that actually have a negative exponent. All right, it looks like we're on number 31 now. It's getting a little more complicated maybe. So we have, I guess this one's not too bad though. It's kind of similar, I guess, to number 26. You have 3 things multiplied inside the parentheses. I see a times b times c, and there's an exponent. But it's more complicated because there's a negative exponent. But still, because everything inside the parentheses is being multiplied, it's a to the negative 2 times b times c to the third. I'm able to distribute this negative 1 power onto everything that's part of the product inside the parentheses. And just like we did in that first problem that we were covering here, we're going to raise whatever power the variable already had, -2 for example, it's going to get an extra power of -1. I guess B didn't have a power, so he'll just have the -1 power that we're distributing. The C had a third power, but he's going to get that extra -1 power. And just like the problem directly above it, this one, number 26, now we multiply powers. If you see a power to a power, they're multiplied now. So for A, I have a -2 times a -1, that's +2. B only had one exponent, so it doesn't need to be simplified yet. C has a power of 3 times -1, that's -3. And now, just like I said in the directions, we don't want to see any negative exponents in our answers. So we'll just look at what we have and say, okay, who has a negative exponent? B does and C does. So they need to go to the denominator. But A can stay in the numerator because it has a positive exponent. So A will be the only thing in the numerator, but B will go downstairs and its exponent will become positive, as will C's, once you move it to the denominator. Then I guess the very last thing would be, excuse me, you can rewrite it with no exponent on B, because anytime you have an exponent of 1, it's kind of just, I don't know, it looks messy and it doesn't need to be there, because anything to the 1 power is that thing. So it's kind of silly to write B to the 1 power, because B to the 1 power is just B. Alright, let's try number 32. This one, I guess, sort of similar because you have a power, but this time we have a quotient inside. There's things being divided or there's a fraction. But still, I think we've said before in the lecture videos, as long as everything inside the parentheses is either being multiplied or divided, no addition or subtraction inside the parentheses, then you're free to distribute an exponent that's outside the parentheses. And since I see inside the parentheses 2 times x divided by 3, yeah, it's all multiplication and division, so I can distribute this -3 power outside onto everything. Onto the 2, onto the x, and onto the 3. And then we'll see what happens from there. So it's 2, that guy gets a -3rd power, the x squared gets a -3rd power. And if you want, you can skip that step of writing that. We know by now that you're multiplying powers. So if right there you just wrote x to the -6, that'd be fine. And the 3 in the denominator also gets the -3rd power. Okay, looks good. So maybe for now I'm going to leave the 2 to the -3rd the same, and the 3 to the -3rd the same. But the x to the 2nd to the -3rd, if I multiply those powers, I get -6. And now that I look at this, I notice everything has a negative power. Oops. So that means that everything needs to move to the opposite side of the fraction. So the 2 that's in the numerator has to go downstairs, the 3 in the denominator has to go upstairs, and the x that's in the numerator has to go downstairs. So it's pretty much like you're flipping the fraction upside down, and you're changing everybody to positive powers. So we got 3 to the 3rd on the top, and then 2 to the 3rd on the bottom, and x to the 6th on the bottom. Alright, and then this is where I think it's okay to leave it like that. Or, since 3 to the 3rd and 2 to the 3rd aren't really that big of numbers, you can multiply those out. 3 to the 3rd is 3 times 3 times 3, which is 27. 2 to the 3rd is 8, because that's 2 times 2 times 2. And then x to the 6th, of course, we can't simplify that because we don't know what x is. So there, I think either one of those I'd be happy with. Unless it explicitly says, I don't know, multiply out any exponents, then I guess the right answer is better. But if they don't tell you how to write your answer, then I think it's hard to tell which of these to write. So I think either one's good. Alright, let's try 33 now. Number 33, I think there's a few ways to approach this. First of all, you could right off the bat move anything with a negative exponent to the opposite side of the fraction and then try to simplify. Or I think for me, the way I like it better is just, I see an 8 and a 12, those are kind of like terms, I can simplify those. I see m's above each other, I can simplify them. And then n, I see an n over an n, and those can be simplified. So for me, I usually take care of the negative exponents at the end. I think taking care of them at the beginning, it's not really worth it, because what if I move everything and then simplify? There's still going to be negative exponents left anyway. So I think moving that m to the -2 to the denominator I don't know how helpful that would be. Although it would work, I think it'd just be different. Let's see, so if the 8 and the 12, what can we reduce those guys by? I guess just 4. 4 can go into 8 twice, and 4 can go into 12 3 times. So all I know is the answer is going to have a 2 on the top and a 3 on the bottom. How about for the m's? So we've seen this before. If I have an m over an m, or the same variable over the same variable, you subtract the powers. You take the numerator's power, -2, and then subtract the denominator's power is 4. And let's see, and again, like we did before, that m is kind of in limbo. It doesn't know where it's going to be. It doesn't know if it's going to end up in the numerator or the denominator until I see whether the answer is going to have a negative exponent or a positive exponent. But now that I see a negative exponent, -2 minus 4 is -6, I can tell that that m is going to go downstairs with the 3. How about the n though? Let's see, n, I'm going to do a similar thing and subtract their powers. 3 on the top minus 7 on the bottom. That'll give me n to the -4. Okay, since that's also a negative exponent, it looks like m and n are going downstairs with 3. I guess 2 is going to be all by himself, poor little guy. 3, okay, then m to the 6 becomes a positive exponent. N to the 4th also becomes a positive exponent. Once you move it, it becomes positive. All right, beautiful. Okay, now we're talking about scientific notation. So I think, to me, scientific notation, it's not really difficult. It's just hard to, I don't know, it's just kind of annoying to remember all the details. But I think for me, if you ever forget which way, I don't know, like if I see this negative exponent on the 6, I say, oh man, I forget, does that mean I move the decimal on this guy to the left or to the right? I think the easiest way to remember it is thinking, okay, if I see a negative exponent like we have here, a -6, that means the number, our number will be getting smaller. So anything with a negative exponent represents a small number. But if I saw a positive exponent, like if that was a +6, my answer should be a big number. So I look at 1.89 and I say, okay, if I move that decimal to the left or to the right, which direction would make me, or give me a smaller number? Well, think about if you move it to the right, that's going to make the number bigger, right? Like if I move it twice, that's 189. If I move it 3 times, that's 1,890. So as I move it to the right, it's getting bigger, but actually since it's a negative exponent, I should be getting a smaller number. That's how I know I need to move it to the left. 6 times, whatever that number is, -6. So yeah, I have a bad memory, so I don't really remember which way to move it. I just think about it and say, which way would make it smaller because I have a negative exponent. Move the decimal 6 times. To the left we decided, huh? So once would move it here, twice, 3, 4, 5, 6. So it should end up here. I have how many blanks? 1, 2, 3, 4, 5 blanks, and then the 189. But remember, if you move the decimal past your digits that are there and there's empty spaces, you always put zeros there. So it looks like I'll have 5 zeros before the 189. And it's kind of up to you. It's up to kind of your taste. Do you just like to see a decimal and then numbers, or do you like to see 0 point? I don't know. I think I remember I was taught to put the 0 in the front. I think because that way for sure you see the decimal point. But it's up to you. I don't think either one of these is better than the other. Either is good. Yeah, it's kind of just up to taste. How do you like it better? All right, that's a good one, number 34. Actually, I hope you don't mind. Maybe we'll do number 36 next because it's similar. Because we're going from scientific notation to standard notation. So this one, you notice though that the exponent in number 36 is a positive number. Positive, so that means that our number should be getting larger. That'll give me a clue as to which way to move the decimal. So this number here, 2.0057. I look at it and I start imagining me moving the decimal to the left or to the right. If I move it to the left, like in the previous problem, this number is going to get smaller. Because if I move it to the left once, that's 0.2. If I move it to the left twice, that's 0.02. So it'd be getting smaller, but I want it to get bigger. So I must be moving it to the right 8 times, whatever this number is here. To the right 8 times. Okay, so I got once, twice, 3, 4. Okay, so 4 times would move it past the 7, but I have to move it 8 times. So it's 4 times 5, 6, 7, 8. It'll land right here. So I'll have 2, 0, 0, 5, 7, and then how many blank spaces? 1, 2, 3, 4, and then the decimal. But remember, like we said in the previous problem, anywhere you see blank spaces, you're going to put zeros. So there must be 4 extra zeros that I need. And actually, you know, if you see a decimal on the very right of a number and there's nothing to the right of the decimal, you can just drop the decimal. Oops. So the answer would just be 200,570,000. You could leave the decimal if you wanted to, but it's just kind of, I don't know, not really helpful, you know? It's like, what if you went to a casino and they said, "Oh, you won $1,000." You'd say, "Ooh, I won $1,000. Look at that." And then what if someone told you, "No, look at this is how much money you won, 1,000 decimal." You'd say, "Yeah, I know. That's the same exact thing. What the heck? You're trying to make it seem better than it is, or what?" Anyway, same thing, but the decimal's just kind of redundant. I don't know why you would even put it there. You can though. I mean, you wouldn't get marked down for it. That's what I'm trying to say, I guess. Okay, I think we're doing good. Now let's try number 35 and 37. That's where we're starting with kind of a normal standard number, and we want to put it in scientific notation. I think to me that's a little more difficult, or harder to remember how to do. But remember, when you're trying to convert to scientific notation, you're not starting with scientific, you're trying to go there. You want to put your decimal directly to the right of the first non-zero digit. That's the hardest part to remember, I think. To the right of the first non-zero digit. And I guess when I say the first one, I mean, if you're looking at this number that you're given from left to right, between the 2, 7, 0, 0, 0, if you're looking from left to right, what's the first non-zero number or digit? Well, it's the very first one. 2 is non-zero. So really we want the decimal to be right after the 2. And you could keep all the zeros, but you don't really need them because any zeros that are at the end of a decimal number don't really help you. Again, that'd be like what if you saw in your bank account you had $2.70 and you thought, "Oh, that's kind of a bummer." And someone said, "No, you don't have $2.70, you have 2.7000000." You wouldn't be very excited. You'd say, "Thanks for trying to make me feel better about it, but that's the exact same number." So yeah, zeros are kind of redundant. I mean, I put them, but I'm probably going to drop them eventually. Actually, I'll probably do it right now because it just looks cleaner without them. So I'll just put 2.7. Those zeros aren't really helping. The first step, yeah, is place the decimal where it needs to be based on what we set up here. But then you have to multiply it by 10 to some power. And pretty much it'll just be whatever number of times the decimal moved. So on the original number, it was 27 billion. And a whole number like 27 billion has an invisible decimal at the very right side. I just need to figure out how many times did the decimal move from where it started to where I moved it. Let's see, it went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think is how many it would need to have moved. Alright, and the very last step would be, okay, now decide, is that exponent going to be positive or negative? But kind of remember what we said in numbers 34 and 36. Remember number 34 we said up here, where is it? Since we saw a negative exponent, that means we're dealing with a really small number. But if like in number 36 you had a positive exponent, you'd be dealing with a large number. So we just have to decide, is our number that we started with large or small? Well, this guy is definitely a large number, 27 billion. So us sticking with a positive exponent is a good idea. It'd only be if we were given a really small number, like if it was 0.00000 something 27, then we need a negative exponent. So we're good. Since we started with a large number, we're going to have a positive exponent. Alright, let's try to do a similar thing now in number 37. The first thing we said was we need to put the decimal directly to the right of the first non-zero digit. So as I scan the number we're given from left to right, the first non-zero digit is the 4, because before that we have all zeros. The first non-zero digit is the 4. And I guess I could keep all those zeros, the 5 zeros, 3, 4, 5, but any zeros in front of a whole number don't really help you. That's still just 4.021. I don't really care how many zeros you put in the front. So this looks kind of messy if you leave them there. I'm going to drop them all. There we go. So that would be where you put the decimal. And scientific notation always has times 10 to some power. Let me see what the power will be. I'm just got to think, okay, the decimal started here, and I ended it here right after the 4. So how many times did it move? Once, twice, 3, 4, 5 times. But since we started with a small number, let's see, Now remember, if you start with a small number, you want a negative exponent. But if, like in number 35, you started with a large number, you want a positive exponent. So the last step would be just throw a negative on that 5 power. Yeah, so we say that's for a small number. Because that's what we started with, 0.000, blah, blah, blah. All right, good. So far, so good, I think. Let's try the next one here. So this one's actually, if you just remember what what degree means for a polynomial, this is probably the easiest problem on the whole practice midterm or the whole review. Remember, degree of a polynomial, that just means what's the largest exponent. And that's it. So if I look at each of these terms, you got a power of 2, a power of 3, and this guy doesn't have an exponent because it doesn't have a variable. So it doesn't really count. I guess this is like a 0 power. So the largest I see is a 3. That must be the degree. And that's really all there is to it. You just say, all right, what's the largest exponent I see in this polynomial? That's the degree. It seems like it should be more difficult than that, right? I don't know. Oh well. All right, I think the rest of these problems are pretty good. You're just kind of combining like terms, and yeah, polynomials are kind of nice in a way. It's almost like a little break from the hard stuff we've been seeing lately. So this problem, what do we have? I just look for kind of terms that have the same variable and the same exponent. So notice that the first and the third terms both have a b squared. And when you combine them, don't forget that you're not changing the variable or the power. So once those get together, I'm still going to have a b squared. You know, it's not like b squared minus b squared is b to the 0. The exponents don't change when you add or subtract terms of a polynomial. All you do is combine their coefficients. So I'm looking at the 3, that's the coefficient of this guy, and then kind of like a 1 is the coefficient of this guy. So I'm subtracting, I guess, because there's a minus in front of this one. So it's like 3 minus 1 would be 2b squared. Yeah, because you have 3b squared minus b squared. That's like 3 minus 1, which is 2. All right, those are taken care of. And for me, I always cross them off so I don't keep glancing at them and thinking I'm still using those. Those are done for. And then how about this negative 6b? He's got a like term later on with b here. They both have the same variable, and they both have kind of like a 1 power, I guess. So they're like terms. But when I combine them, of course, the power's not going to change, and the variable's not going to change. It's still a b. I'm just combining their coefficients. We got the negative 6 from the first one, and this guy's got a 1 coefficient. Negative 6 plus 1 is negative 5b. Yeah, kind of thinking of this as 1b. Negative 6b plus 1b. Negative 6 plus 1 is negative 5. And then lastly, the easiest part is just the numbers that don't have a variable, kind of like the constant terms. A positive 7 and a negative 10 make negative 3. There, and then of course, the only detail in these is that if at all possible, you want to try to write these in descending order of powers. So notice we had the highest power, b squared, and then the kind of middle one, b to the 1 power, and then the constant term that's kind of like a b to the 0 power last. So I guess that's the only thing you want to check on these is, if it's possible, write these, yeah, from a descending order of powers. All right, that was good. How about the next one? We got, yeah, very similar. They just kind of put these parentheses around it, and yeah, you notice. I don't know if you notice in the homework and everything. Section 4.3 and 4.4, they have a lot of really similar problems, and you kind of think, wait, why? I mean, why are there two separate sections if we're kind of doing the same things? I think in section 4.3, looking at the problems that we had here, it kind of looks like it all started as one big old polynomial, just with all these terms mixed up, and some of them are like, some of them are not like, but it all started as one polynomial. So I think that's the difference. And then in section 4.4, they're giving us maybe 2 or 3 separate polynomials, and that's what the parentheses indicate. But it still kind of amounts to the same thing. Because just because you have parentheses around this guy and parentheses around this guy, The only thing you'd have to worry about is, well, is there something in front of these parentheses that I need to distribute? Not really in this one, because a plus doesn't really change anything. It's positive 5x. And then a positive on a negative still makes a negative. So that, yeah, this one you can just drop the parentheses and not worry about much. But if this was a minus in the middle instead of a plus, that's when you'd have to really worry about distributing that minus onto the rightmost polynomial. But now that I've removed the parentheses, this is a problem just like the previous one. Now just see what are the like terms. Well, I noticed that 3x squared, there are no more x squared terms other than him. So he has no one to combine with. He'll just kind of stay the same. But the negative 2x and the 5x can combine into a 3x. And the 6 and the negative 3, 6 and minus 3 is 3, positive 3. And that's in descending order of powers, which is good. The squared term, the 1 power, and then the constant. Let's try the next one. Number 41. So that one has a negative, or a subtraction sign. That'd be the only thing I'd have to worry about. I have to distribute this negative or subtraction onto everything in the second parentheses. But the leftmost parentheses, there's nothing to distribute. I mean, there's nothing in front of the parentheses, so I can just drop them without worrying about anything. But if I distribute the subtraction sign onto the second parentheses, it'll make negative 2x and then plus 1, because it was a negative on a negative, which makes a positive 1. But once I do that, now it's all just looking at like terms. 9x minus 2x makes 7x. And then the 6 and the 1 makes 7, positive 7. There we go. And that's it. And that's in descending order of powers, because you got a power of 1 for the first term, and then the second term is a constant, so it kind of has like a power of 0. That's a good answer. Okay. I think we're ending with the best problems here, huh? So far, I don't know. I never minded these types of problems at all. They're kind of nice. As long as you're careful. Yeah, just be careful. Number 42, it just has more terms, but still it's similar to the previous one. We're going to distribute this negative power onto all three of these guys. No need to do anything to the polynomial on the left, because there's nothing to the left of its parentheses to distribute. But I have to change everybody's sign on the right, because a negative on a 10x squared will make it a negative 10x squared. The negative on the negative 3x will make it a positive 3x. And this negative on the positive 5 will make it a negative 5. And now I just look for like terms. I see 4x squared minus 10x squared. That'll make negative 6x squared. Then we have negative x plus 3x. That's like negative 1 plus 3. That's 2x. And the last guys, we got negative 7 and negative 5. Those make negative 12. Beautiful. And that's in descending order of powers. Good. Okay. So how about the next one? I like this one because there's a plus in the middle. So you could think of it as distributing the plus, but a plus doesn't change anything. So I can really just remove the parentheses altogether. T to the 9th plus 3t to the 6th minus 8t squared plus 5t to the 7th minus 3t to the 6th plus 8t squared. And this one, to me, since there's so many different powers here, I usually glance and look around, what's the biggest power I see, or the highest power? I think t to the 9th. I think it's good to do that, to look for the highest power, because you want your answer in descending order of powers. But that guy has no one to combine with. There is no other t to the 9th, so that guy will stay as is. And then after he's done, cross him off. What's the next highest power? It looks like the t to the 7th, huh? But he also has no one to combine with. There's only one t to the 7th, the 5t to the 7th. So that's done. Scanning around, it looks like the next highest power is the 3t to the 6th, but 3t to the 6th minus 3t to the t to the 6th cancels. There's nothing there. Yeah, because 3 minus 3 is 0. And then after that, all that's left are a couple like terms. Negative 8t squared plus 8t squared is another 0, because negative 8 plus 8 is 0. So all that's left is the t to the 9th and the 5t to the 7th. That's kind of... That one I might think I did something wrong. It's like, wait, too many things canceled. That seems too good to be true. But I think they designed this problem like that. Okay, so far so good. Let's try this next one here. Ooh, I gotta be careful, because I do see a subtraction sign in the middle. So he has to be distributed onto the very right polynomial. The left one, though, I can just drop the parentheses. 3a to the 4th minus 9a to the 3rd minus 7, let's see now. If I give that negative sign or the subtraction sign to the 4a to the third and the 13a squared, they'll become negative. But then if I give the negative to the negative 3, it'll become positive 3. Gotcha. Okay. If I scan through all these terms, the highest power I see is this 3a to the fourth. And he doesn't have a like term to combine with, so he'll just be staying as is. Done with that. The next highest power are the third powers. Negative 9a to the third minus 4a to the third. So if I combine the coefficients, it's negative 9 minus 4, that's negative 13a to the third. So I've combined them, they're done. The next highest power is the a squared, but he doesn't have a like term, so he'll just stay as is. Negative 13a squared. And all that's left now is the negative 7 and the positive 3. See, negative 7 plus 3 is negative 4. There we go. And then just because we were scanning for highest powers as we went, we know that our answer is going to be in descending order of powers like we're supposed to have. So that's a good sign. All right, that's a good one. All right, this last one, at first I kind of get worried, like, oh man, there's fractions. But I think the fractions will interact so that it won't be too bad. So the first parentheses I can just drop because there's nothing to distribute. But the second parentheses have a negative in the front, so I better distribute the subtraction or the negative sign, and then I can drop the parentheses. The x to the 6 will become negative, but the x to the fourth, it's a negative on a negative, so it's now a positive x to the fourth. And then the negative on the positive half x will make it a negative half x. Yeah, we notice the negative in the front of a parentheses just pretty much changes everybody's sign, right? It was positive x to the 6, now it's negative. It was negative x to the fourth, now it's positive. It was positive half x, now it's negative half x. So yeah, just pretty much changes everybody's sign. Now with all these terms, I'm going to scan what's the highest power I see, the x to the 6th. And that one does not have a like term, so he'll just stay as is. Negative x to the 6th. The next highest power, I have some x to the fourths. And it's like, think of it as a 1. You have a 1x to the fourth plus 1x to the fourth, that's 2x to the fourth. So combine those guys. Now the next highest power is this negative 2x squared, and he doesn't have a like term, so he'll just stay as is. Alright, but once he's gone, what's left? Just the negative 1 half x and negative 1 half x. Unfortunately, those will not cancel because negative 1 half minus 1 half is not 0. If you want, you can go off to the side and think about it. You're combining their coefficients, right? Negative 1 half minus the other 1 half. And those do have the same denominator, right? So we don't have to find a common denominator. We're just ready to combine those. We got negative 1 minus 1, that's negative 2. So it's negative 2 over 2, but negative 2 over 2 is negative 1. So that ends up being our last coefficient, negative 1x. Which actually makes sense, because if you have a half and another half, what if you take two halves of something? A half and a half make a whole. So that kind of makes sense that we got a 1, even though it's negative. I think my very last step would be I'm going to drop that negative, or the 1 actually. Because remember we said if you ever have a coefficient of 1, it's redundant and it's not simplified all the way. Because 1 times anything is that thing. So I'm just going to write minus x instead of minus 1x. Yeah, if you have a 1 in front of your variable, it's not simplified all the way. It'd be like if you left, 1 times 5 as your answer in some other problem. I'd say, why'd you leave it as 1 times 5? Why not just multiply them? 5. That's your answer. It's kind of similar. 1 times x, you know it's x, so why even write the 1? Alright, I think that's good. So hopefully that made sense. If you have any questions, please let me know. Please email me or call or I guess whatever. Or yell really loud. Maybe I'll hear you all the way from my house, 45 minutes from Modesto. You better yell pretty loud though. That's all. Really loud. Anyway, why am I so weird? Alright. I'll talk to you guys later. Hopefully that helped. Thanks for listening.